Hey everyone, this is Mr. Lehan Teaches You Stuff. This is Grade 9 Chemistry Lesson 6, the Periodic Table, Part 1. So this is what the periodic table looks like, and it has every single element that we have ever found in the universe. It is on this table, and this table is arranged in a very specific order. If you look down at the bottom, you'll see that there's a box that's somewhat separate from the rest of the table. It starts off with number 57 and number 89 right underneath it. That box is actually supposed to be part of the rest of the table. And if it's put in where it's supposed to be, the table actually looks like this. So this is what the periodic table should look like. But we just take those two rows out and shove them underneath the periodic table just so it fits on pieces of paper or posters that you'd put up in a classroom easier. But this is the actual look of how the elements should be arranged on the periodic table. Now I'd like to go over a little bit of the history of the periodic table. Early on, scientists tried to organize the elements into some groups or order, but ran into several difficulties. They couldn't arrange things alphabetically, because every time they found a new element, they'd have to rearrange the entire list. So alphabetical order didn't seem to work. They couldn't organize things by color because so many of them looked the same. So here's several elements here, and they all look pretty much the same. You would have a hard time figuring out which one's which just by looking at them. They also couldn't use taste to discriminate between the elements because many of them were quite poisonous. If you tasted some of them, you would just die. Then along came a Russian scientist named Mendeleev, and he found that if you arrange the elements based on their chemical properties and their atomic mass, a pattern emerged. So Mendeleev used his knowledge to create a periodic table, and he even left spots open where he knew other elements should exist because an element with certain properties of a certain mass had not been found yet. So for example, element 31 right here, gallium. Gallium had not been discovered when Mendeleev made his table, but he left a spot open for it because he knew there should be something there of a certain weight with certain properties. And he was able to correctly predict its atomic mass, its density, its melting point, and how it would react with other chemicals before anyone else even knew this thing existed. So this was a big deal because scientists had not been able to make predictions about undiscovered elements before. So when Mendeleev did it, it seemed almost magical, and everyone quickly adopted the periodic table. Now we are still filling in blanks of the periodic table today. On May 30th, 2012, 2 elements were added to the periodic table. So number 114 and 116, flerovium and livermorium, were added in 2012. So if you look at this periodic table and you compare it to one that's probably hanging in a science classroom, you might notice that this one has more elements in it, and that's because a lot of the older periodic tables are rather out of date. So this one's up to date as of right now in 2013. They are So we're still filling in the blanks of the periodic table. And if you look down at the bottom right hand of the table, you'll see several elements seem a little out of place. These ones have 3 letters in their chemical symbol instead of 1 or 2. And these are just placeholders. These ones have not actually been found. So 113 is ununtrium, which stands for 113-ium. 115 is ununpentium, which stands for 115-ium. 117 is ununseptium, which is 117-ium. And 118 is ununoctium, which of course is 118-ium. So I'm sure you get the pattern there. And keep in mind that these are just placeholders. We haven't actually found these elements in real life. In each box of the periodic table we have, they'll get a proper name. The atomic number, which remember is the number of protons. And we'll get rid of the 3-letter chemical symbol for those. There's the chemical symbol right there. There's the element name underneath the chemical symbol there. We have the atomic mass, which remember is the number of protons plus the number of neutrons. And we also have the ion charge up at the top right. So if you want to know how many protons an element has, all you have to do is look at the atomic number. So in this case, 17. If you want to know how many electrons an element has, it's the same as the number of protons and the atomic number. So the number of electrons is 17. If you want to figure out how many neutrons there are, you need to take the atomic mass, that's the big number, and subtract the atomic number, which is the smaller number. So just remember, big number minus smaller number, and you'll be good. So we take 35.45, which we round up to 36, and then we subtract 17, and we end up with 19 neutrons. So chlorine has 19 neutrons. So let's do a couple more examples. How many protons, electrons, and neutrons does boron have? Well, boron has an atomic number of 5, which means it has 5 protons. That also means it has 5 electrons. Next, we can look down here. It has an atomic mass of 10.91. We need to round that up to 11. So we take 11 minus the 5 protons, and we end up with 6 neutrons. So boron has 5 protons, 5 electrons, and 6 neutrons. All right, we'll do one more example. How many protons, electrons, and neutrons does cobalt have? Well, cobalt has an atomic number of 27. So it has 27 protons and 27 electrons. Now cobalt also has an atomic mass of 58.93. So we'll just round that up to 59. And then we do 59 minus 27, and that gives us 32 neutrons. So I just want to point out that we don't use the ion charge in the top right there, that 2+. We don't use that at all to calculate the number of neutrons. So cobalt has 27 protons, 27 electrons, and 32 neutrons. So now let's take a look at chemical symbols. Chemical symbols always consist of either 1 or 2 letters. Now the first letter is always capitalized and the second is always lowercase. And this is to prevent confusion. So for example, CO does not equal CO. The first CO there, you've got capital C, capital O. That's carbon and oxygen, and that's carbon monoxide. And it does not equal capital C, little o, or lowercase o, because that's an element, that's cobalt. So carbon monoxide is not the same as cobalt. Since there's lots of elements out there with the same first letter in their name, some use letters from their Latin name instead. So let's go through a few examples where the chemical symbols are very different from the name of the element. So first off, we have Hg, which is Mercury's symbol, and that Hg comes from the word hydrogyrum, which is Latin for liquid silver. So if you ever see Mercury, it looks like basically liquid silver. Silver, on the other hand, is Ag, and that Ag comes from the Latin argentum, which means silver. Au is gold's symbol, and the Au comes from the word aurum, which is Latin for gold. Now sodium, its symbol is Na, and Na comes from natrium, which is Latin for sodium. And natrium actually comes from the French word natron, which is basically baking soda. And baking soda contains sodium, so that's how it all sort of mixes together there. Pb is lead, and the Pb comes from plumbum, which is Latin for lead. Or actually, sorry, that's not Latin for lead, it's Greek for lead. And the Greeks used to use lead to make their pipes. And that's also where we get the word plumber from. And last example is Fe, and that's iron symbol. And Fe is, or it comes from ferrum, which is Latin for iron. So how is the periodic table arranged? Each element has an atomic number that represents the number of protons an atom of that element has. So we knew that already. But as you go left to right across the row, the atomic number increases by 1 for each element. So the first element at the very top left, hydrogen, it has 1 proton. The second element, with the atomic number 2, it has 2 protons. And then 3 protons, 4, 5, 6, 7, 8, it goes up like that. So that's how these things are arranged. So that's it for this video. Tune in to our next video, the periodic table part 2, patterns in the table.